Greetings. In this video, I'll be doing a couple of more examples on finding the inverse Laplace transform using algebraic manipulations. We've done partial fraction decomposition, and we've also talked about putting constants to match the inverse Laplace transforms. Let's look at the following example. So let's say I would like to find the inverse Laplace transform of, sorry guys. Let's say I want to find the inverse Laplace transform of 5s over s squared plus 6s plus 11. Okay, well, I do know the Laplace transform for sine and cosine, and the Laplace transforms are either a variable over s squared plus a squared or a constant over s squared plus a squared. And this denominator looks like that, but it's not in a perfect square form that I need it to be. So, and I can't factor 11 and 6. So therefore, the best thing I could do here is to try to complete the square. So let's go through the process. So Laplace inverse of 5s s squared plus 6s plus, now if you recall, completing the square, you take the coefficient of the coefficient of s, you divide it by 2 and you square it. So 6, the coefficient of s is 6. 6 divided by 2 is 3. 3 squared is 9. So you add 9 to complete the square, and you subtract 9 to balance what you've done. Because remember, overall, you can't change the given exercise. You could just make it look different. Anyhow, so this will make the first three terms a perfect square. So this becomes Laplace inverse of, this becomes Laplace inverse of 5s over s plus 3 squared plus 2. And that's my completing the square results. Now here, remember, you look at this Laplace inverse. Now if this was, forget the 5 as a constant, it's going to be able to come out. So think about it. If this was Laplace inverse of s, and I'm just going to throw this out there, s squared plus 2. If this was Laplace inverse of s over s squared plus 2, you would have said, okay, well, that's simple because that's just the Laplace transform of cosine of at, cosine of rad 2t, right? Where this is 2 is a squared. So, and this looks very much like that. The only difference is, you notice instead of s, you have an s plus 3, and let's see if you recall something. You recall that the Laplace transform of, remember, e to the at f of t? Remember the shift? The Laplace transform of e to the at f of t was f of s minus a, which basically means that the Laplace inverse of f of s minus a is e to the at f of t. Which means that all you have to do if you're trying to find a Laplace inverse of a function in S domain which has a shift to it, all you have to do is ignore the shift, just find the Laplace transform of f of s. That will give you f of t, and then just take this shift amount and put an exponential next to that function with that shift. So if that's the case, then what I need to see here is that I need to see, I'm going to change color here, I need to see this 5 taken out because it's a constant, and I need to see a plus 3 sitting next to s here so that I can have a nice shift, so I could actually then simply write the answer as cosine of rad 2t and evaluate it at the given shift value. So let's see if we could do it. So I'm going to change colors again. Okay, so I'm going to pull the 5 out because that's a constant. I can simply do that. Laplace inverse of. Now I have s, but I need an s plus 3, so I'm going to say a plus s plus 3, and I'm going to do minus 3 to undo it. And what I have in my denominator is s plus 3 squared plus 2. Now I could separate this, so I have 5 Laplace inverse of s plus 3 over s plus 3 squared plus 2. And I can just put brackets there. Laplace give minus 3 Laplace inverse of 1 over s plus 3 squared plus 2. So it becomes that. Now here, it looks like it's much doable than before. Now this one now, it has the nice shift applied to both the denominator and the numerator, so they have the same shift. So here I could just write, well, that's just, and I'm going to keep the 5 on the outside. So I'm going to say 5 times. Now Laplace inverse of the first expression, that's just the cosine of rat 2t, but shifted with a negative 3 units. So all I have to do is just put an e to the power of negative 3t next to it. And that's what the shift does in time domain. So a shift in frequency domain produces a multiple of an exponential with that shift. Now minus, now here, this looks like a sign, but in order for this to be a sign, if I have an a squared at the bottom, I have to have an a on top, which means what I need here is a multiple of rat 2. Which then to undo it, I have to put a rat 2 on the outside. So this becomes negative 3 over rat 2, Laplace inverse of rat 2 over s plus 3 squared plus 2. So this is simply sine of rat 2t. And again, you have a shift to negative 3, so you just have a product, like a factor of e to the negative 3t. And that becomes my inverse Laplace transform. Very good. Let's try one more example. Let's take the Laplace inverse of s over 2 plus 5 over 3 divided by s squared plus, let's see, s squared plus 4s plus 6. That's right, that's what I needed to say. Okay, so now, again, I notice I need to complete the square, so let's see what we'll do here. We'll have, it's pretty much the same example, so I'm going to drive through this a bit faster. So I'm going to write this as 1/2 Laplace inverse of s over s squared plus 4s plus 6 plus 1/3 Laplace inverse of sorry, that's a 5/3, my bad. That's 5/3 Laplace inverse of 1 over s squared plus 4s plus 6. So I have 1/2 Laplace inverse of that plus 5/3 1 over Laplace inverse of 1 over s squared plus 4s plus 6. Now, what I would do here is I would complete the square. Again, you notice a cosine coming out of the first one, right? And a sine coming out of the second one. So s squared plus 4s plus 6. So make it nicer. So 4 divided by 2 is 2 squared is 4. So I add 4 here. Alright, and then close the curly brackets. Plus 5/3 Laplace inverse of 1 over s squared plus 4s. And same here. Plus 4 and minus 4. And I need to adjust that. Sorry. And close parentheses. No curly brackets. Alright, so this becomes 1/2 Laplace inverse of s over s plus 2 squared plus 2 plus 5/3 Laplace inverse of 1 over s plus 2 squared plus 2. And again, you notice the same thing is happening as you had to do for the previous exercise, which means here you notice you have a shift of negative 2 units. So what I will do is I'll put a plus 2 and then a minus 2 will have to go in there. And then I will have to put, and in this one, it's a constant, so I'd have to multiply this by rat 2 and multiply this denominator by rat 2 to adjust it. And a cosine will be coming out of this. Well, this will split. So a cosine and two sines are going to come out of this. So I'm going to write this a little simpler. I've already done the separation for you, and it's identical to the last exercise that I just showed you. So I'm gonna leave a few steps to you to do. Okay, so you continue with some steps until you try to bring it to this point. So now I'll write it a bit more simplified. So I have 1/2 Laplace inverse of s plus 2. I haven't skipped too many steps, maybe 2 steps. S plus 2 squared plus 2 minus 1 over rat 2 Laplace inverse of rat 2 over s plus 2 squared plus 2 plus 5 over 3 rat 2 Laplace inverse of rat 2 over s plus 2 squared plus 2. So that's what you end up with. Okay. Now here I have 1/2 Laplace inverse of s plus 2 over s plus 2 squared plus 2. So that's just, again, cosine of rat 2t e to the negative 2t, which represents the shift in the frequency domain. And then if you combine the other two together, because it's the same Laplace inverse, minus 1 over rat 2 plus 5 over 3 rat 2, you just get plus rat 2 over 3. And then that's a simple definition, inverse of that is simply sine of rat 2t. And you have to introduce the exponential that incorporates the shift in frequency domain here. So that becomes your inverse Laplace transform. Thank you.